Hello class, this is a supplementary video for our discussion on Chapter 3. So Chapter 3 was where we started to add in a few scripts to get the player shooting around the scene, but also getting the enemies to fire back at the player. So the meat and potatoes of all that was a script called the Wandering AI script. So here it is. For a refresher, it does two things. It fires a fireball at the player, but it also moves the enemy around. So what I'm talking about is in regards to the Wandering AI script. Instead of having one script do all the movement, instead of having one script do all the functionality that is required of the enemy, we decouple that. So there's a concept in computer programming and I guess computer science in general, and that is the idea of decoupling code. So instead of having one script that does everything, we have several scripts that each do one main thing. So here we can decouple our Wandering AI script functions of moving and firing at the player so that we have two separate scripts for that. So let's begin with the fireball. So the fireball shooting script, we can decouple the functionality of shooting at the player into a separate script called fireball shooter. So it's going to fire at the player. Okay, so it's a little bit more involved. It is based on a two-state state machine where we have two states that are, say, allowed to fire and, say, not allowed to fire. So here we have, as before, we have a field for our fireball prefab that we want to fire at the player. We also have several fields here. The first one is the sphere cast radius that's set to default 1. A detection range that is how close must the player be before the fireball shooter starts firing at the player. In this case, it's set to 5 meters. I now have a cooldown. So the cooldown is as follows. The moment I fire a fireball at the player, a countdown timer starts ticking down. Once that timer reaches 0, I can fire another fireball. And if I make this interval really short, I basically have a machine gun. So, and of course we have the another field for the current cooldown. It might be a good idea to differentiate between your private fields and your public fields. There are several conventions to that. I think one of them is putting an underscore in front of any field that is private. Again, whatever conventions for coding that you use, be consistent with them. And I'll do my best to do the same. So I'm going to try to have private fields have an underscore from here on out. Yeah, I'll do my best to do that. Okay. So this is a two-state state machine where we are paused or allowed to fire. We also need a private field for the firing state. So when this script starts, the cooldown is going to be set to 0, and it's going to say, okay, we're allowed to fire now. I also have I have a method that changes the state. So this script is going to be referenced by the reactive target script. So if this is attached to the enemy, it's going to grab a reference to the fireball shooter, and it's going to change its state to paused when it is hit. So it'll stop firing then. And the update method, it's about the same. So the update method now has this raycast related code that only executes if it's allowed to fire. So only do this code if it's allowed to fire. But let's continue on. The first thing we do is to calculate our current cooldown. So if our current cooldown is a non-zero number, we're gonna decrement an amount of time that is time.delta time from that cooldown. Once it reaches 0, we don't have to do any more of that. So it'll only tick down if there is time left on the countdown timer. When we do comparisons, when we compare floats with floats, oftentimes what you think is like 1.1000000 can actually be 1.1000003 or something like that. And that's because floating point variables are just weird like that. This is what I call floating point weirdness. Sometimes there's a little bit that sometimes there's just a little bit of that variable that is just off. So if we want to make comparisons between two floating point variables, we don't use something like current cooldown equals 0f. We instead say something like if mathf dot approximately, and then we pass in our current cooldown and 0f after that. So it's going to compare the two, and if they are close enough, by close enough I mean there is a internal value called an epsilon that when these two values are compared against one another, they are going to be within an epsilon of one another. So if that condition is met, when those two values are sufficiently close enough to one another, we're going to evaluate this expression to true, which actually evaluates to false because we're negating it. But basically, what this says, if our current countdown timer is not already 0, we're gonna count down that countdown timer until it reaches 0. So we decrement current cooldown by time.delta time, and this is to make sure that when it reaches 0, it is 0. So just in case time.delta time, ticks down and it becomes negative, this f.max, make sure it stays 0. And then after that, it's the same raycasting code as we had before. Well, technically it's a sphere cast, but so it's the same as before. We're going to perform a raycast. We're going to detect whether we hit the player. And if we do, we're also going to see whether our current cooldown timer was already 0. And if so, we're going to shoot a fireball at the player. Very simple. So in the Wandering AI script, there was already a private field for the fireball. We have no such field over here. It's only in here. So that way, that way the fireball shooter script basically doesn't keep tabs on any fireballs that it shoots. They're just gonna go off and do their own thing. All the fireball shooter script cares about is whether it can fire again, regardless of whether the fireball it had shot out previously had despawned or not. So in the Wandering AI script, it can only ever shoot one fireball at a time. There can only ever be one fireball in existence. Well, by that I mean, if it shoots a fireball, it cannot shoot another fireball until the previous one has already despawned. Here, it will shoot a fireball only if the countdown timer has ticked down to 0 again. So that is the fireball shooter script. And the idea behind this decoupling is, now we have a fireball shooter script that is decoupled from movement. We can make a turret out of it. So previously we have made this spinny cube for experimental purposes. If I take this improved script and I put it in its own folder, I'm going to take the fireball shooter script, attach it to the spinny cube here. If I then get the fireball prefab and put it in this slot here, if I press play, check that out. We have a spinning turret that really isn't doing all that good of a job. It's missing the player consistently, but that is probably because the sphere cast radius is a little bit too big. So let's set it to something narrower like 0.3, and let's decrease the fireball cooldown by a lot. So let's say 0.05. So every 1/28th of a second, it's going to shoot another fireball. Hopefully this thing is slow enough that with spinning that it'll hit the player multiple times. Let's see. not quite. Maybe I have to set it even slower. There we go. We got a machine gun. But I think for best results, we want to make smaller fireballs. We can change the scale of the fireball because it's a prefab, and that'll just change the scale of every prefab that we make thereafter. But yeah, we have a fully functional turret. We could use this in our games. Anyway, now we have a decoupled. Now that we have a decoupled fireball shooter that we can use for things that don't need to move around, let's consider what happens when we decouple fireball shooting and wandering movement, and consider the other counterpart, that is decoupled movement. So I've called this one smart movement, and I call it smart movement because it is smarter than the previous iteration that we have here. So it has 5 states. So the first state is, of course, the paused state, new movement allowed. The next one is pretty self-explanatory. It's allowed to move. It can move forward. The third one is a blocked state. That it'll only enter the blocked state if it had encountered an obstacle. Once it's at that state, it's going to make a decision to either turn left or turn right. For now, that's just based on a coin flip. But regardless of whether it's rotating left or right, it's going to look for whether its path is clear. And when it does, it's going to re-enter the moving state and start moving forward again. So there are quite a few fields here. There is a rotation speed, pretty self-explanatory. There's a movement speed, also pretty self-explanatory. There's a sphere cast radius, also self-explanatory. That's for use with the sphere cast. There are 2 obstacle ranges, so it will block itself from moving if it is too close to an object, but it will only move if there is enough distance from it and another obstacle to start moving again. So by default, these are 3 and 5 meters. So if this object were to encounter an obstacle that is less than 3 meters away from it, it will stop moving and rotate, and it will not move again until there is at least 5 meters of space between it and the next obstacle. And much like the wandering AI script where we had to have a method to change whether it's alive or dead, we have something similar where we change the movement state and we just pass in a new movement state. We also have this detect obstacle method here. It's basically the raycast code, except it returns a distance to the nearest obstacle, where if it finds an obstacle, it's going to return how far it is, or return -1 if the obstacle is way too far. Or -1 if there are no obstacles, I should say. Here's where it gets interesting. So here, I'm not using update anymore, I'm using fixed update. So it turns out if you are using update, if you are doing physics calculations, you want to use fixed update instead. The reasons for that are a bit nuanced, but basically this is to make sure that all physics calculations are done perfectly in sync. So instead of the update method, we want the fixed update method. When we use fixed update, instead of multiplying by time.delta time, we want to multiply by time.fixed delta time. So here is where that state machine starts to shine. So we have blocks of code that are only executed for each specific state. So if we are allowed to move, we're going to move forward, and then we're going to detect for obstacles. If we find an obstacle that is way too close to us, we're going to block. And by block, I mean it's going to block itself from moving, and now it's no longer allowed to move. That's not to be confused with the paused state. So once it's paused, it can't be unpaused until something else unpauses it first. So the blocked state is when we encounter an obstacle, we're going to decide whether to rotate left or right. And once again, it's just based on a coin flip, so I'm basically generating a random number that's either 0 or 1. If it's 0, rotate left, otherwise rotate right. Pretty simple. The code for rotate left and rotate right are nearly identical except for a single minus sign. So we're going to detect an obstacle. And if that obstacle is still too close to us, because we need ample room to move forward. If that obstacle is still too close to us, we're just going to keep rotating. Otherwise, if we encounter an obstacle and it's sufficiently far enough that we can comfortably move out of the way, we are going to change our state back to the moving state. So yeah, this is a state machine. Much like how the fireball shooter is a state machine. So the fireball shooter is a two-state state machine. It's either allowed to fire or it can't fire. The smart movement script is a multi-state state machine where it has several states related to movement plus the pause state, which says not allowed to move right now. So I've changed the reactive target script so it gets references to both the smart movement script and the fireball shooter script. So the wandering AI script originally encompassed both functionalities of moving and firing at the player. Here we're getting references to both scripts. So get a reference to the smart movement script if such a reference if there is such a component, we're gonna pause that. Do the same for the fireball shooter script. If a shooter script is attached, pause that. So they're paused if the reactive target is hit. And when it does, it's gonna die. So much like as before, if the enemy gets hit, we need to stop it from moving, and then it dies. Pretty simple. Okay, so let's see the cumulative effect of all of these scripts together. So I have about 30 smart enemy scripts in the adjacent room over here. I have already changed some of their values to be a little bit different. So instead of just a reactive target script, which is getting references to these two scripts here, I also have the smart movement and fireball shooter scripts attached. So again, the point of decoupling movement and shooting is so we can mix and match functionalities. We can have things that move and shoot. We can have things that move but don't shoot, and we can have things that shoot but don't move. Let's check it out. So all of our enemies are in this room here, and it's kind of like a gas right now. So it's like a gas whose gas molecules are slowly dispersing into the outside space. So right now they are spinning in place because they can't find space to move. But there is a little opening in which enemies can start to move out. When they do, they start to realize, oh, there's space now. And now they start moving around, and look, check that. When they encounter an obstacle, they spin on the spot until they find a path that has sufficient space for them to move forward. Look at that. They're moving around. How neat is that? And oh, they're all the way over here now. So yeah, this is what you get when you have, well, a smarter AI for our enemies. How neat is that? We have enemies that can better react to their surroundings. I guess another way we can improve these things is to have not one sphere cast, but actually 3 sphere casts. So when we are in the block state, we could, for example, be smarter on whether we should turn left or right. So there would be 2 additional sphere casts that detect which direction is clear. So if I do a sphere cast that's slightly to the left, and then I do another sphere cast that's slightly to the right, whichever sphere cast reports a lower distance, that is the direction I turn away from. So instead of flipping a coin to determine whether to turn left or right, we do 2 more sphere casts, one each to our sides, and then whichever reports the lower distance is the direction we turn away from, or rather, whichever reports a higher distance is the direction we turn towards too. I needed that. Anyway, these are some ideas that I hope would inspire you to write not only more cleaner code, but to further experiment with what you want to do for your game. So the point of this class, the point of game programming is, well, it's more the programming side of what it takes to make a video game. I highly encourage you to experiment with this game. Yeah, we're doing this all in a 3D environment. Maybe you want to do a 2D game, but let's focus on the 3D aspects for now, because it's just more interesting and satisfying to see. I guess you can consider this satisfying, but a lot of what we're talking about can apply to a 2D context as well. It's just that a lot of the components that we have that are working in 3D, there are a lot of companion components that work in 2D. So for now, we're gonna mainly focus on the main 3D project here. And how many times has the player been hit anyway? Can I see the player's health? No. But man, the player's being hit constantly. And that's because we have a turret. This turret is programmed to spin on the spot and fire at the player if the player is detected. So yeah, how neat is that? We have decoupled the fireball shooter script. So that's really the only 2 things that are different with this project. Apart from the minor changes that we made to reactive target, we have 2 new scripts here. And again, all of this is to just demo what we can do if we decoupled our scripts and made them a little bit smarter. So if you want to work with this script for yourself, I'm gonna let you pause it and copy the script for yourself if you need it. So here's the update method. Line 59 is the end of the code. So that is the fireball shooter script. A lot of it is the same code from the Wandering AI. Really, the biggest changes are the one to the smart movement script. So here is the beginning of the code, lines 1 to 31. I have a few fields that aren't being used, so you can just omit those if you don't want to deal with them. I wanted to randomize the rotation and movement rates, so everything just has a little bit of variance to it. The idea behind that is so that way they're not perfectly synchronized with one another in case they are coincidentally moving at the same pace, like next to one another. So here is the fixed update method here. It's a bit involved. Here's the rest of the script here. So 63.92. Pause that if you need it, and there we go. And once again, here is that reactive target script. Really, the main changes are these 7 lines of code here. So it works the same as with getting a reference to the Wandering AI script and setting it so it's dead. Here, we're just pausing them instead. There we go. Right. So that's the entirety of what I want to talk about with regards to Chapter 3 and experimenting with the code. I'm gonna leave it off for now, and then I guess next chapter we're gonna think about adding textures and 3D models to the scene. Okay? Alright, thank you. Bye.